All right, next up is number 6 in 13.7, which says to consider the sphere x squared plus y squared plus z squared is 49. So we have a sphere centered at the origin with radius 7, and here's our point P with coordinates 2, 3, 6, and in part A it says to find the equation of the tangent plane to the sphere at this point P. So you can imagine this little tangent plane here that comes in and just touches the sphere at this one point P. Okay, so to help us get started here with the geometric solution, I'm going to go ahead and just draw in this position vector. I'll call it V. And notice since V starts at the origin and ends here at the point P, its components would be 2, 3, and 6. And if I take a look at this cross-sectional view of our sphere, and here's our position vector, and here's our point P. Oh, here, I'll move this a little bit, and then here's that tangent plane cutting through like that. Okay, the fact that our surface is a sphere, so in other words this cross-section is just a circle, would then imply that this position vector V would be perpendicular to this orange tangent. Okay, so you can think about just shifting this position vector V up a little bit, and we're saying that this vector would be perpendicular to this tangent line. But of course, if it's if we have perpendicularity here, right? I mean, we're really just saying, look, we have perpendicularity here for the plane. Okay, so let's make a little note of that. We're saying that this position vector V is, I'll just say perpendicular, so upside down T there, remember means perpendicular. It's perpendicular to the tangent plane at the point P with coordinates 2, 3, 6. Okay, so why is this a useful thing to observe? Well, if you recall from Calc 3, this is back in section 13.1 on page 855, if you know a vector that is normal, or in other words perpendicular, those two words, normal and perpendicular, are synonymous, and let's say that vector, I'll call it n, has components a, b, c, and you know a point on your plane, P, with coordinates x naught, y naught, z naught, then you can write down the equation of the plane as follows. You do a, the I-coordinate of the normal vector, times the quantity x minus x0, plus b times y minus y0, plus c times z minus z0, and that's all equal to 0. Okay, so what we're really saying here with this little cross-section argument is that this vector v is in fact a normal vector for our tangent plane, and its components, recall, are 2, 3, 6, and the point P that we're given on the surface, so on the tangent plane as well, is just our point P 2, 3, 6. All right, so then I can just immediately write down the tangent plane equation using this result from 13.1. So that would be 2 times x minus 2 plus 3 times y minus 3 plus 6 times z minus 6 is 0. And I'll go ahead and multiply this out and move stuff over. I'm going to get 2x plus 3y plus 6z is equal to what? Well, on the left side I'd get a minus 4, minus 9, minus 36. That would be 49 when you bring it over to the right hand side. Notice that 49 is the same right hand side as our original sphere equation. If you give it some thought, in fact if you chose any point P on your surface and applied the same argument, you're always going to get a 49 over there. So maybe think about why that is true. All right, cool. So that does it for part A. So now what I want to do is look at the next part, which is really to just find the equation of the tangent plane again, but now we're going to do this using a gradient vector. Okay, so how exactly do gradients come into play here? Well, what we're going to do is we're going to look at this left-hand side, our x squared plus y squared plus z squared, and I'm going to think about this thing as a function of 3 variables. So I'll call that f of x, y, z. Okay, so if this is our function of 3 variables, then what can I say about this thing in relation to our sphere? Well, our sphere, of course, is just x squared plus y squared plus z squared. So in other words, f of x, y, z, and then we're equating that. So this would equal this right-hand side, which is 49. Okay? And the reason why I'm pointing this out is that this thing is what? Well, if I set the function equal to a constant, right, the set of all points that would satisfy this equation is what we call a level, not a level curve, right? This is a function of 3 variables. This would be a level surface of this function f. So here's the key insight to solving part B, where we're going to use a gradient, okay? We're now thinking about our surface, which is this sphere in blue, as one of many level surfaces for this function we're calling f, right, which is just the left-hand side of the sphere equation. Okay, so our right-hand side, right, because a general level surface is just of the form f of x, y, z is equal to c, right? So if I set that right-hand side to 49, I'm just going to get, right, our sphere. If I set it, say, to 48, I'd get a sphere of radius root 48. If I set c, the right-hand side, to 50, it'd be a sphere of radius root 50, so on and so forth. Okay. So why is this useful? Well, recall when we looked at gradients for functions of 2 variables, we said that if I look at the gradient at a certain point, then it's perpendicular to the level curve of our function that passes through that point. Well, that same kind of result holds for functions of 3 variables. Okay, if I'm at a point, which in this case we're at this point P here, which I'm going to label right here, 2, 3, 6. Then it turns out, really by the exact same argument that we applied for functions of 2 variables, that the gradient vector for this function f will be perpendicular to this level surface here in blue that passes through this point P. Okay, so let's go ahead and record this. This is a theorem in the text, and it says that if f is differentiable at a certain point and the gradient does not vanish at that point, then the gradient is perpendicular to the level surface of f that passes through that point. Okay, so here is the big takeaway. The takeaway is this. This theorem is implying now, in particular for us, that the gradient of this function f at the point 2, 3, 6 is perpendicular to the sphere, or I'll say our sphere, just to make it more emphatic, at the point P. But if this gradient vector is perpendicular to our blue sphere, right, then in particular we can say that this gradient must then also be perpendicular to the tangent plane at our point P. Okay? That's the big takeaway, right? Because again, if I just draw a little picture here of our sphere, and then we're at this point P, and here is our tangent plane. Our gradient vector, if it's perpendicular to the sphere, then it will also be perpendicular to this tangent plane. Okay, so again, what we've done is we've generated a normal vector to our tangent plane, and so then we can just fall back on that result from section 13.1 to write down the equation of this tangent plane. And let's go ahead and do that, right? So what is the gradient vector for this particular function? F of x, y, z is x squared plus y squared plus z squared. Well, the x derivative is 2x, the y derivative is 2y, and the z derivative is 2z. So if I plug in the coordinates of our point P, this then would be 4, 6, 12. So now we can go ahead and say, all right, for our tangent plane, okay, we're going to do what? Well, for the I component of this vector that's normal to our plane times x minus the x coordinate of the point on our plane, which is just P, so that would be 2, and then plus 6 times y minus 3 plus 12 times z minus 6, yeah, and that's 0. Now if you go ahead and open stuff up and clean up, you of course will get that exact same thing that we got before. This would still come out to be 49. So the answer is the same as it should be. But the other thing I want to point out here before we wrap this up is that notice here the gradient, if I factor out this 2, I get 2 times the vector 2, 3, 6. And what is this vector right here? This is that position vector we used in our solution using geometry. Okay, so if V was perpendicular to our tangent plane, then certainly 2 times it will still be perpendicular. And there you go, all right? Now, in the next video, which will be our last for this section, we'll show how we can use this theorem to write down the equation of a tangent plane for any surface that's implicitly defined. In other words, z is not solved for here in this equation, and that'll lead us to a nice result for surfaces of that form. All right, see ya.